Hello, so today we're gonna do something a little bit different from what we usually do. So we're gonna start a lesson called calculus. And firstly, limits. So what are limits? Limits are a very important thing when we have to learn calculus. What does that? What do we mean by that? So let's look at what are limits. Limits is basically something you get really close to. Yeah. So let's say for the first question, not really a question, but it's like a example. I have two functions. Firstly, y equals to 2x minus 1. The second one, y equals to 2x minus 1 times x minus 2 over x minus 2. Now, what's the difference between these two functions? Basically, for the first function, it is defined, within the interval that we give. It's basically from 1 to 4, which I didn't draw from, but it's okay. And then the second one, x cannot equal to 2. Why? Because the denominator cannot be 0. Yeah? So the function we give here is actually undefined at x equals to 2. Okay. Now, what is the beauty of limits? What is limits trying to see? So basically what limits is trying to see is what the value of a function is as it approaches, as x approaches something. Let's say as x approaches 2. We know that the function is not defined at x equals 2. But as we can see, as it really approaches, but x doesn't equal to 2, it can cancel out. Right? When x doesn't equal to 2, it can just cancel out. So the function looks like a function of 2x minus 1. So if we look back at a 2x minus 1 function, as x equals to 2, the y value equals to 3. So when x approaches to 2, the y value approaches to 3. Now that's what the limit is trying to see. It's trying to see what the value of the function gives as x approaches something, as the input approaches something. Right? Now let's look at the second example. I should have started with this one, but it's okay. Let's look at these two lines. So the first function is y equals 3. The second one, 3x minus 9 over x minus 3. Now what's the difference between this? Firstly, I can factorize the second function into 3 times x minus 3 over x minus 3. So it's the same example. X is undefined at x equals to 3. Okay, but what if we're looking at the value of y as x approaches 3? Approaches but doesn't really touch. So when it approaches, we can cancel this out. So it's basically the same thing as the function on the right, which is y equals to 3. So when x approaches 3, y value equals to 3. Yeah, approaches but doesn't represent the value of the function. So which means that here, the limit of a function and the actual value of the function might not be the same. Right? For this instance, the value of the function doesn't exist, but the limit exists. Yeah, the limit exists at y equals to 3. Okay, so for another example, what is the limit of g of x when x approaches 2? So g of x is the function that I've drawn here. So at x approaches 2, we can just see like intuitively approaches, right? As it approaches, it reaches a value of 1. But the actual value of the function g of x is actually 2. So g of 2, as defined on the graph, equals to 2. But the limit, here's the notation. The limit as x approaches to 2, g of x, equals to 1. Yeah? So they're essentially not the same because 1 doesn't equal to 2. You may see some sketchy proofs on the internet, but it doesn't prove that that 1 equals to 2. Okay, so now let's look at a notation. So again, if we do this, we write this notation as the limit, right? Limit of f of x, right? Of the function as x approaches a equals to a value of L. So that's how we read it. The limits of f of x as x approaches to a, this one, equals to L, equals to the value that we got here. So the same with the example. The limit as x approaches to 2, so the limit of g of x as x approaches to 2 equals to 1. Same thing. So let's look at some examples. For this first one, the limit of x cubed as x approaches to 3. What does it mean? Well, basically, because we know that x to the x cubed is literally a function that is continuous everywhere we can see, so we can just plug in the value of x equals 3. So if we plug it in, 3 cubed equals to 27. And now the second example, the limit of sine x as x approaches to pi. Well, if we can recall, the function of sine, it looks like it's a wave. It looks like a wave, yeah, with here as 2 pi, here's a 0, and here as pi. So we can see that sine is continuous over this region, so we can just plug in sine pi inside, so it's 0. Well, this should be part of your trigonomics or pre-calculus course, but we're not going to cover it here, so probably in future videos. Okay, now let's look at the graph. I have a function f of x, and what is the value of the function when x approaches to 4? Well, just look at the graph. If we have the function f of x, and here is 4, x equals to 4, it doesn't have a value. It's undefined at x equals to 4, but the function does come to a value. Like, it does approach a value when x approaches to 4. Now, what's the value? The value is y equals to 4. So the answer is 4. Okay, now I hope you understand well the intuitive meaning of limits. And if you don't quite understand, you can rewatch the video for a bit, and I hope you guys can understand what's covered. In the next video, we're gonna cover how do we know a limit exists. Yeah, sounds like an intriguing question for the next video. See you guys. Bye bye.